The p-value method for hypothesis testing uses a sample test statistic that separates the significance region of alpha from the not significant region. This is different than the traditional method that uses the critical value to separate regions. Let's use an example of a right-tailed test. In a right-tailed test, your z-score would be to the right of 0, and we would shade that region to the right. Your probability is associated with your sample test statistic. When we're working with the probability, remember that your probability values are always between 0 and 1 inclusive, and we usually work with decimals. But your values could also be fractions or percents that we then also have to convert. Instead of labeling the shaded region as a rejection zone of alpha, we label it as our p-value, or the p of z equals with some question marks. We will then make our determination based off of the comparison of our p-value with our significance level. You're going to reject the null hypothesis if your p-value is less than or equal to your significance level alpha. We will then fail to reject the null hypothesis if the p-value is strictly greater than our significance level alpha. Let's look at a few examples where we're going to use both the p-value method and the traditional method to determine whether we are going to reject or fail to reject our hypothesis. In our first example, we are given that the alternative hypothesis is the proportion of adults who think a self-driving car is safe is greater than 25%, and a test statistic of z equals 1.18. With a 90% confidence level, we want to make a determination regarding the null hypothesis. They're giving us information about an alternative hypothesis and asking us to make a determination about a null hypothesis. So the first thing that we really have to do is we need to translate what the null and alternative hypotheses look like for our population. The alternative hypothesis H sub 1 is working with the proportion greater than 25%. So we're going to use our little lowercase p greater than 0.25. Remember that even though 25% is sometimes used, it's most common to change these into decimals. That means that our null hypothesis is going to be the proportion that is all the rest of the number line, or the less than or equal to the 25%. Since our confidence level is 90%, that also gives us a significance level of 10%, or an alpha of 0.10. I'm going to separate out my different methods so that way you can see how each one is done. Let's first look at the traditional method on the left. Since my alternative hypothesis is using a greater than symbol, we're going to be working with a right-tailed test. That means I'm going to have a shaded zone over here to the right of 0 where I need to find the critical value that determines that boundary. I can label my rejection and my fail to rejection zones right now. To find my critical value with an area to the right of 0.10, I'm going to use my INV norm. Rounding this to 3 decimals, I get that my critical value is 1.282. I can now place my test statistic somewhere on this graph in relationship to that critical value. Since my test statistic of z equals 1.18 falls between 0 and my critical value, it falls within my fail to reject the null hypothesis region. This means that my value of, or my null hypothesis, that the proportion of adults who think that self-driving cars are safe is less than or equal to 25%. I would fail to reject that. Let's look at how we would make a determination using the p-value. Both of these tests must yield the exact same determination. So it doesn't matter which test you are doing or which test you're asked to do, they must both give you the same answer. It's also a good way to check to see if you're on the right track, because if you do something wrong and you get 2 different answers, you need to check your work again. So I'm still working with a right-tailed test, so I'm going to shade a region to the right of 0, and I'm labeling my test statistic of z equals 1.18 because when we are sectioning off using the p-value method, it's the test statistic that determines that boundary, not our critical value. In order to make my determination using the p-value, I need to find this region. To do that, I'm going to use my normal CDF. In this case, I'm looking for the probability of a z-value that is greater than 1.18. Calculating out our normal CDF, we get that the probability is 0.1190. I can now make my determination using the p-value. Using either the inequality of greater than or less than or equal, I need to compare the p-value that I just found of 0.1190 to my significance level alpha of 0.10. My probability is greater than my significance level. This is going to lead me to the conclusion that I'm going to fail to reject the null hypothesis. Again, notice that when I'm making a determination using the p-value, I get the same result as if I am using my test statistic and comparing it to my critical value. Let's look at another example. Given the alternative hypothesis that the proportion of Oreo cookies that do not meet company standards is not equal to 15%, and a test statistic of z equals 2.78 with a 95% confidence level, make a determination regarding the null hypothesis. We want to be able to create our symbolic notations using the population parameter, inequality type symbols, and in this case a decimal value representing the proportion. Since we're working with a proportion, we're going to use a lowercase p. Now our lowercase p is really the Greek symbol rho, but because it looks like a p, that's what I'm trying to tell you. Just like the mu is the same thing as your mean and sigma is the same thing as standard deviation, you have a Greek symbol that represents the population proportion called rho. Since they're using the notation not equal to, we're going to use our alternative hypothesis that rho is not equal to 0.15. That leaves our null hypothesis that rho, or population proportion, is equal to 0.15. Our significance level is the other 5%, or 0.05, and because we're using the not equal to symbol, this means we are going to have a two-tailed test. Again, let's start with the traditional graph and then work our way towards the p-value graph. With our traditional graph, we need to be able to find our critical value that represents those shaded area boundary lines. Those shaded areas, again, are going to be our rejection of the null hypothesis, while the value or the area in the middle is our failing to reject the null hypothesis. Finding my right critical value, I have a z-score of 1.960. Remember that because of symmetry, I don't need to actually do the work to find my negative, I can just write that in. Another thing to remember is that the critical value I found, you cannot write plus or minus of that value, since this area to the right and this area to the left only yields this positive value. I can now identify my test statistic of 2.78 as being to the right of one of my critical values and in my rejection zone for the null hypothesis. So currently I'm rejecting my null hypothesis, and I'm going to use my p-value to confirm that. In a two-tailed test, when you put your test statistic on your graph, you also need to then add in the negative version of that to show the boundary line of the other section of the rejection area from your traditional graph. I now need to find the p-value. The p-value is going to be the combination of both of these areas combined. Since your calculator can only find values to the left or to the right or in between, in this case what you're going to need to do is do 2 times one of the zones. So finding twice the area of one of those zones is going to yield a p-value or a probability of 0.0054. It's important that you do 2 times one of the zones rather than finding the zones individually and adding them together. Because of rounding errors, you may not calculate it 100% correctly. We can now make our determination using the p-value. I am going to be comparing my p-value I just found to my significance level. While I know that 0.0054 is less than 0.05, when you are making your determination, you must either say it's either greater than or less than or equal to. One option must have the equal to inequality, and in this case it's always the less than option. This is going to leave us with the conclusion that we're going to fail to reject the null hypothesis, which is the same as what we had when we had the traditional graph.